Our lesson today contains two topics. The first is called net change, and that's actually one of the first interpretations we learned about the integral. So we're going to reinforce our understanding about that. And the second topic is called average value. So we'll learn how to use a definite integral to find the average value of a function. I'd like to start by completing this first table, which is a list of all of the interpretations that we've learned about the integral, and the last one is going to tie it back to this thought of net change. We first learned that the name of the symbol is the integral, so when you see that elongated s, it's called an integral, and the literal meaning of the symbol is sum or total. So we started by approximating integrals by using values on a table, and that gave us the total amount over time. Next, we learned how to interpret the integral of a graph of a function by finding the area between the function and the x-axis. That gave us the exact amount of change over time in comparison to when we approximated over a table, it was just an estimate or an approximation. Then we connected the idea of area to a function's antiderivative, which is what we find when we're given the integral of a function. And the antiderivative is notated with a capital F of x for a function f of x. All of these interpretations of the integral actually lead us back to the same basic idea that when we integrate a rate, and so I've pointed out that the derivative of f here indicates a rate of change, we end up with the net change in f of x over time. And by net, we mean that it adds up all the positive and negative change that has happened over time. So the simplest way that you can think about that is the integral of a rate of change gives us the change over time. In this next table, I'd like to make a list of all the formulas that we know based on the concepts we've learned, including the new formula for today, which is average value. I think it's nice to see them all in one place because they have similarities and differences that are nice to point out. Our first concept is net change. It is also referred to as accumulation, which is another way of saying you're adding up all that positive and negative change. And you might recognize the formula as the fundamental theorem of calculus part 1. It is the integral of f prime, and it equals f of b minus f of a, so that's how we evaluate that integral. It means the change in the function over time, interval a to b. And the units, since what you're getting is a subtraction of the function values at a and b, are going to have the same units as the function f of x. The instantaneous rate of change is one of the first concepts we learned in the first half of calculus. It's otherwise known as the derivative, and when we started learning about IROC, we learned this limit formula, f of x minus f of c over x minus c. But now that we have all of our shortcuts for the derivative, like power rule, product, quotient, things like that, we can kind of skip over this longhand formula and go right to our shortcuts. So the meaning is the derivative. Graphically, it is the slope of a function f of x at x equals c. And whenever we take the derivative, you're taking those units of the function and you're dividing by time. The average rate of change, or AROC, has the similar setup as the difference quotient in the instantaneous, but it does not have the limit. So all it does for us is give us a good estimate or approximation of the derivative. And since we're approximating the derivative, it's going to have the same units as the derivative, which is the units of the function divided by time. This next concept is the second topic of our learning target today, so it's a new formula for you. It's called the average value, and the way that you calculate it is 1 over b minus a times the integral from a to b of f of x dx. And when you first see that, you might not think of that as an average, but let me explain why it actually is. To find the average of any set of numbers, you add them up and you divide by how many numbers there are. Well, what we see here is the integral, which is a sum of values, and we're actually dividing it by b minus a. All we've done is actually take that constant and move it out of the integral because of that property that allows us to do so. So we have a sum divided by the interval, which gives us the average value of a function on a to b. And since it's an average value of a function, it has the same units as that function itself. So you'll definitely see some examples of that average value formula so you get used to how to set that up and solve it. Our last concept in the table is one that you learned a long time before you reached calculus, but just wanted to make a complete list. It is a function value, so when you're asked for a function value, you would find f of c, which is different, of course, than f prime of c. So you're just finding the y value at some c x value, and those units would be the same as f of x because it is a value of the function f of x. What I'd like to do in this next table is actually look at those concepts again, but use a very simple example to illustrate so you can visualize and start to sort out the differences between these concepts and also to apply the formulas. So to find the net change of our function of x equal to x on the interval 0 to 4, we would take a look at our graph, and relating back to what we talked about up here, because our function is not a derivative, we would just need to use the right side of this formula, which is f of b minus f of a. So in this case, you would get f of 4 minus f of 0. From your graph, the point at 4 would be 4, and at 0 would be 0, so that difference would be 4. And that tells us how much the function has changed over the interval. So the y value was 0 at the beginning, and at the end it is 4, so that change would be 4. To find the instantaneous rate of change at 3, we would need to think first about the derivative, and of this simple function x, the derivative would just be 1. So the derivative at 3 would also be 1 because there's nowhere to plug the 3 into, and that gives us the slope of this function at x equals 3. So if you go up to the function at x equals 3, confirm the slope is 1, and that's true because the slope of the entire line is 1. If we apply our AROC formula to this function, we end up getting 4 over 4, which is also 1. So the average slope of this function is 1. Again, that's true for a linear function because the slope is constant throughout the line. But for any other function besides linear, it's more than likely true that these two numbers, the IROC and AROC, are not going to be the same. But since we picked such a basic example, they happen to be both 1. So let's apply this new concept of average value, our formula for the first time. So 1 over b minus a would be 1 over 4 minus 0 times the integral from 0 to 4 of f of x dx. So I get this 1/4 from that fraction in front, and I have the integral of 0 to 4 of f of x dx. And since I'm looking at a graph, I could go ahead and find the area. If you were more inclined, you could actually find the antiderivative just about as easily. It would be x squared over 2. But let's use the graph to find the area of that triangle. So I've got my 1/2, my base height are both 4, and so the resulting area would be 2 when you make all those multiplications, and that gives me the average y value on 0 to 4, which I think you can agree that if you look at all the y values from 0 to 4, right in the middle, the average would be 2. I just want to make a quick side note about the average value formula that I think is a neat geometric connection that you might be able to see. If you look at our average value that we just did, we got 1/4 times that integral, we got 2 as our average value. I want you to think about multiplying both sides of that equation by 4, which would cancel that out. It tells us that the area under the function is 8, and what that does is it actually gives us the area under the average value function from 0 to 4. And so if you found that rectangular area, that indeed would be 8. So what it does is it takes that blue area and kind of smushes it down into a rectangular form, and that area is always equal at exactly the average value, which I think is pretty cool. So just to finish our table off, we have the function value at 3 would be f of 3. That happens to be 3 because it is the 0.33, and that is the y value at x equals 3. So let's finish by looking at our first example of average value. We're going to set it up and then try to put it in our calculator. Okay, it asked me a pretty direct question. Find the average value of this function y on the interval -1 to 3. So right away I have my a and b values. So I do 1 over b minus a times the integral from a to b of that given function. And let's talk about how you'd put that in your calculator. So if you have a calculator, try to follow along with me. I've got the 1 over 3 minus -1. Of course, you can make that 1/4 if you feel comfortable. And then right away, we'll hit that Math 9 menu, get our integral typed in. So it's all going to be entered at once. and that should give us a final answer.